Hello and welcome. Today we're looking at The Odds Are Odd, a statistical test for detecting adversarial examples. So shameless self-promotion here, since this is me. So this is an archive, and basically what we do is we're detecting adversarial examples. For those who don't know what an adversarial example is, it's basically a way of fooling a classifier in order to kind of get it to do something weird. Let's look at it. So maybe you have an image of a cat. And yeah, I have no clue how a cat looks. Alright, so you have an image of a cat and you have a classifier, alright? So the classifier takes this image as an input, kind of winds it down to some probabilities of classes, and cat, dog, and so on. And it then gives you an estimate of how likely each class is, right? And so on. So what an adversarial example does is it changes this image and it adds a noise. So this is just a very specific noise. And you have kind of a multiplier here, gamma, which is super small. So the noise is almost, you can't see it with a human eye, basically. It's so small. But it's able to perturb this image in a way that the probabilities will change such that all of a sudden a different class now is the highest class. So basically we're able to fool these classifiers by adding just very little bit of very, very specific noise. So that's an adversarial example. These have many implications in, let's say, security applications and also in understanding how these classifier works. Right, so our task is to explain and detect them. Explain why they happen and detect when they happen. All right, so what do we do? Right. Basically, let's just jump right into the thing here. We view a classifier as an output. So you have logits, what's called logits. L is this. This here is your neural network up to the last layer. Basically, it can be like something like a convolutional neural network and so on. This gives you a feature representation. So you extract from the image X a feature representation, which is this entire thing here, and then you multiply this feature representation. So this is going to be some vector of dimension D. You multiply this by this weight matrix, which is going to be something like, okay, I've drawn it in the wrong direction here. Let's draw W over here. It's going to be D by, let's say, K, where K is the number of classes. Okay, still wrong. D by K, right? And output a vector of dimension K, which then is this cat, dog, and so on. So these are the logits, and the logits get transformed to the probabilities by running it through a softmax layer. But basically, we view a classifier as having a feature representation and a weight matrix, and this here is a matrix multiplication, a dot product by matrix. So what we see basically is this is kind of where the adversarial examples happen. So when we look at this weight matrix, right? Again, we look at the d-dimensional feature vector here, and we look at the weight matrix. What it does is it has columns, right? Columns. Let's say we have 4 classes here, right? So it has these 4 columns. And each of them is d-dimensional. So each of them is going to be multiplied by this thing, and giving a score. So the final score for a class is going to be the multiplication of a row W1, W2, W3, W4 by this feature vector. Let's call the feature vector little f. Right. So your logit of class I is going to be the inner product of Wi and f. All right, we'll leave away biases for now. There's okay, we can introduce biases to make it a bit more complicated, but it changes nothing. So your logits are going to be the inner product, and whichever logit is the highest wins. So that's going to be the prediction of the classifier. So since you can, in an adversarial example, what can you change? You can change this feature vector here, this f. By changing the x, you can change the output of the convolutional neural network, which is the feature vector. And what you have to do in order to make a logit as high as possible, basically make one class as high as possible, is you need to make this inner product as high as possible. And what's an inner product? If you look in like a classic vector representation space, if this is W, I, and this is F, what you want to do is you want to make F and W align as much as possible, because the inner product is going to be basically dependent on the angle and the magnitude. So you can stretch F for sure, but it's going to be kind of aligned with all the W's then more by stretching, or more negatively in whatever way you want it. But basically you want to rotate, you want to align as much as possible the F with the Wi. So you want to kind of go into this direction with F. So now, not only do you want to kind of maximize F with a particular Wi, what you want to do is be adversarial. The adversarial task is often framed as just, it's either targeted, so so I needs to be a particular other class, or it's untargeted, which means just give me a perturbation that will make the classifier be fooled. And be fooled means whatever it predicts right now, it should predict something different, right? So what you ultimately want to do is you want this as high as possible for some I that is not the correct I, and you want this other quantity, Wi, let's call it Wi, if, let's say the classifier is 100% correct. So Wi, Y is the label of X, right? Wi is whatever column here is currently predicted. So you want the sum column, where I is not equal to Y, to have maximum inner product, and so this is no longer Li, we'll get to that, to have maximum inner product, and you want this inner product with the correct class to be as small as possible, which ultimately means you want this entire quantity maximized. So it's a pretty simple idea. We'll call, let's say this is the logit I minus the logit Y. We have slightly different notation in the paper. I think we call this Z, but never mind. So you basically just want to make this as large as possible. And so our point is, since this is not the only thing, you want to maximize this, but you have a constraint. Namely, your constraint is that your delta x can only be small, right? Your delta x can only be small because the point of an adversarial example is that the perturbation is so small you can't see it. And that means that you basically don't have much wiggle room to do these perturbations, which means that we should be able to detect a pattern like this in the latent space. So this here is the latent space feature vector, and if we can kind of detect a pattern in the latent space, then we kind of get the adversarial example detector. All right. So how do we do this? We measure exactly this. What we do is we measure the alignment between the currently predicted class and between all other classes. So in this graphic here, you see this. It's a 10 class classifier. This is CFAR 10. We only show we only show 6 of the other classes, but we have the full graphic in this. So this shows an adversarial example. The axis going on top of each of the images is the alignment with the adversarial class. So this has been an adversarially perturbed sample. So this shows the alignment with the adversarial class. And of course, you see the bright red dot. If you just focus on that, that is the adversarial example, right, projected into this. So of course the alignment is going to be very, very high with this class, since the classifier actually predicts this class. The blue here is the sample that the adversarial sample was derived from, which means the original image, kind of. And you already see, without looking at any of the other dots, that the blue is around 0 here, around 0 here, around 0 here, here, and here. But here, it's very high in this axis. So the axis to the right is for each of these plots here, it's one of the other classes, except for the currently predicted adversarial class. So that this axis is always the same axis, while the axis to the right for each plot is a different one. And you can already see, and that's why we frame it in the green, this plot here is where the axis to the right corresponds to the original class of the classifier. Right. So don't look yet at the other plots. What you see here is basically the blue is really high in this class, right? And the adversarial example procedure basically has driven it down this class and up this class, which is exactly saying it has made this inner product small and this inner product large. So where do we go from here? Let's actually jump this graphic a bit and go to this one that's way down here. All right, so what we've done is we've taken an example just out of the data set, right? And then we've taken an adversarial example. So let's say X is the example of the data set, and then X hat is the adversarial example derived from this. All right, in this plot to the right, X would be sitting about here. And I'm going to explain what the kind of meaning is. And X hat would be sitting down here, right? It's about 1/3 from the top, 1/3 from the bottom. Well, let me draw this more. All right. So what this axis represents here is basically what we've done is we've gone from X to X hat in very small steps. And at each step, we've asked the classifier, hey classifier, what's the probability of the class Y? So Y is the class of X, right? And the class of X hat is some different some other class, right? Since it's an adversarial example, we've asked the classifier, what's the class of X? And basically we've asked what's the probability that Y is the class of X, and that's represented in white, right? So the more white, the higher the classifier thinks the class Y is probable. So the direction down is going into the direction of x hat minus x. So it's going into the adversarial direction. And then the direction across is, we've taken some direction that's orthogonal to this direction, and then also went into tiny steps and asked the classifier, hey classifier, what do you think is the probability of y here? So we've basically done this kind of grid sampling, and at each point we've asked the classifier, what do you think, how probable is y? And the classifier will always output some number, and we plot it in white. And so this direction, again, is always the same. In this direction, we basically randomize it and then aggregate it over lots and lots of different samples. And we also aggregate this entire thing over the data set, so we get a comprehensive view of what adversarial examples look like in the view of the classifier. And what we find is pretty interesting. So when you go from the original class, you basically, in every direction here, it kind of, the original class kind of decreases smoothly, right? You see at the edges here, it kind of gets black. So the further away you go from the original example, the more, the kind of shadier the classifier gets. It's like, yeah, I'm not so sure anymore that this is the class, right? But if you go into the direction of here, if you go into the direction of the adversarial example, the kind of drop-off is, first of all, it's very steep. So all of a sudden, here, you're in very dark territory, which means the classifier doesn't think y is probable at all anymore. And moreover, you get this kind of cone here. So what we see is, what we think is happening is that, given an example, there are these directions in image space, basically, straight directions that go to adversarial examples, right? And we call these cones because they're kind of low-dimensional directions in the space where the adversarial example lies. And what's really interesting is, we have those plots here. Do we have more? So what's quite interesting is that, here. If you go, come on. Well, this is kind of okay. The quality of the plots is not very good. So I may be able to draw this here. So if you start here and you go here, what happens to the original class is you start out high, you go down rapidly, and you stay down. Even if you go super far into this direction, this class will stay down. Whereas, let's say this is y hat. Y hat will start low, go up, and then kind of fade. So here is where the adversarial example would sit. Sorry, at about this distance. That's this distance here. Means as you go towards the adversarial example, right here, the probability of the adversarial class rises and the probability of the original class drops. Then as you go further, this is what's interesting, kind of, this probability here drops, which means the classifier is kind of like, yeah, okay, there's too much noise now, I'm not so sure about this class anymore. But this class here kind of stays low, very, very long, even if you go into this direction. So this gives us kind of a hint that adversarial examples are characterized by specific directions that you go into that you can go into and kind of suppress the original class and pump the new class up, which is kind of exactly what we've claimed with this inner product alignment. Right. The next experiment we've done is we've taken this adversarial example here and said, well, if we go outside, if we go into random directions, right, it's just really this one direction that's problematic. If we go into random directions, actually we should be, go back to the original class, right, since it's basically surrounded by the original class. This is just one direction, and this here represents all the other directions there are. And how many directions are there in pixel space? Like, a lot. So we should be able to get back to the original class, but that's not the case. We found that's not the case, and we also found why. So still want to go back to this plot here. If you do this, if you add noise, and this is the noise magnitude here, what you'll see is the orange here is the adversarial class. So orange will go down. Down, 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 right? As you increase the noise. The blue is the source class. So the blue goes up, and it goes up faster. You see, it goes up faster than the green, which is the highest other class. So green is whatever class is not the adversarial, not the source, but the highest class other than that. So the source class goes up quickly, but before the source class can overpass the adversarial class, which happens back there, the highest other class has already kind of taken over. So the source class is basically too weak, and if you again look at this plot here, if you go with an actual color picker, you see that the amount of white here and here is not high enough. It's like 0.3 or something out of 1, or even lower. So the kind of source class is not strong enough that by simply adding a bit of noise you can go back. But we thought, hey, if this is correct, we can actually detect this effect here, this rising of the source class faster. So our plan is basically we add noise, a particular amount of noise, just a little bit actually, and then we detect which class falls and which class rises. And the way we do this is we detect this exact alignment that I've described before under noise. So we form this quantity here for all classes other than y. So y is the class that's currently predicted, and we look at it, what happens under it, under noise, right? So, and that's where we get to this graphic here. So again, this axis is the adversarial class, or the class that's currently predicted, right? This axis here is all the other classes for each plot 1. And when we add noise, what you see is the noise magnitude is encoded in the brightness of the dots. So the darker the red dots, the more noise we've added. Here is the original adversarial sample. Then as we add noise, you see here, more noise, more noise, more noise. Nothing's really happening for the if it's just like one class that has nothing to do with the original class. It simply kind of goes down, simply kind of gets less sure about this class, right? But in case of the original class that the adversarial example was derived from, it really rises, it really kind of, at the same time that it drops, it rises into that direction. So we're able to measure these deltas here under noise, and we're able to devise basically statistics of what happens to these quantities under like if it's not an adversarial sample versus what happens to these quantities if it's an adversarial sample. So here you see pairings of basically source class and adversarial class samples. So each of these histograms is collected from that. And what you can see is in blue the kind of alignments under noise of the source class. The alignments under noise of a non-perturbed sample, and in orange the alignments under noise of an adversarial sample. And what's cool is that these alignments you can see in all of these cases are very different. So there's a clear signature in the adversarial sample in these noise-induced alignments with the weight matrix rows that makes you able to basically build a detector. You can say, all right, anything to the left is clean, anything to the right is adversarial. And we can do this over many different types of noises and then build basically a voting mechanism on that and thereby detect adversarial examples. So we have a bunch of experiments. We mostly experiment on the C410 and on the ImageNet dataset. And you can see, where do we see? Here. So this is the main one of the main results, the detection rates of our statistical test. So as you can see, our detection rate, this is on clean samples. So on clean samples you want the detection rate to be low. On adversarial samples you want the detection rate to be high. And we achieve very large detection rates while having very low false positive rates, especially on ImageNet. So it seems like the more tuned these models are, the better these models are, the better we are at detecting adversarial examples to it. It's kind of a direct correlation to how well the models perform on accuracy in a clean setting. And what we can do is now, since we can not only detect these things, but we can detect these things in a fashion. So if you look at these things and you have like a sample of a particular class that's predicted, right? Let's say this class, and you go and look at it at the position of the noise-induced features over each of them. So let's say here, 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 right? You can then clearly say, well, not only do I detect an adversarial example here, right? I look at each of the classes that it could be derived from, right? If all of them say it's a clean sample, then all right, it's a clean sample. But if one of them says it's an adversarial sample, then not only do I know it's an adversarial sample, but I say, aha, this must be the source class, right? This is the exact effect we saw here, right? We can, if we detect this pattern here, we can also back deduce basically, aha, so this must be the original class that the adversarial example was derived from. So we're basically able to build not only a detector, but we're basically able to reconstruct the original class. And here you see for these models, let's say on C410, ImageNet is a bit too large as of yet for our compute, but on these models that have clean accuracies that are pretty high on C410 plus this kind of toy network here, we're able to reconstruct the original class. So basically this is defense against adversarial examples by getting to almost clean accuracy back. So this is really surprising actually, and kind of nice. So we do a bunch of other experiments, including we defend against an attacker that's actually aware of this thing. But the main point here is we don't say this is kind of the end all method of defending against adversarial examples. We simply want to kind of encourage the way of thinking of these kind of noise. What if you noise induce perturbations? How does your network react to that can you detect these effects here? Can you detect effects like this? And are these unavoidable, or are there architectures? Are there architectures we can basically build such that adversarial examples have no chance except doing something like this, which we can then easily detect? Alright, so that was a bit of an introduction. If you like it, check out the entire paper, and goodbye.